ISS Fire Station to explore the tops of thunderstorms presented by Science at NASA. We all know what comes out of the bottom of thunderclouds: bolts of lightning. Jagged columns of light plunge earthward, heating the air to 50,000 degrees Fahrenheit, about 5 times hotter than the surface of the sun. Claps of thunder announce this process somewhere on Earth as often as 50 times a second. Have you ever wondered, though, what comes out of the top? In recent decades, researchers have discovered some strange things happening in the cloud tops. High above ordinary lightning, exotic light flashes known as red sprites, blue elves, and blue jets shoot toward the heavens, cold cousins to the fiery bolts below. In some places, jets of antimatter fly upwards, triggering the detectors on NASA's orbiting high-energy observatories. And, as often as 500 times a day, Earth briefly mimics a supernova, producing a powerful blast of gamma rays known as terrestrial gamma ray flashes, or TGFs. No one knows exactly how these phenomena are related either to each other or to the lightning down below. A new experiment called Fire Station on board the space station aims to find out. Fire Station is a package of sensors designed to explore the links between TGFs, ordinary lightning, and sprites. The space station's orbit will carry Fire Station directly above thousands of active thunderstorms during the 1-year lifetime of the experiment, says Principal Investigator Doug Rowland at NASA's Goddard Space Flight Center in Greenbelt, Maryland. The ISS is perfect for this kind of research. Unlike previous experiments in upper atmospheric lightning, Fire Station has the unique ability to observe thunderstorms at multiple wavelengths simultaneously. It can record the radio static from lightning, measure its optical glow, including the red and blue light of sprites, elves, and jets, and detect the gamma rays and electrons associated with TGFs and antimatter events. Rowland expects Fire Station to observe up to 50 lightning strokes per day, at least one TGF every few hours, and a large TGF every couple of days. Such a fire hose of multi-wavelength data will allow researchers to sort out cause and effect connections impossible to see in previous studies. There are several different types of lightning, Rowland says. At the moment, we don't even know which type produces a gamma ray flash. Fire Station could solve that decades-old mystery in its first few weeks of operation. The thing that intrigues Rowland most about TGFs is their surprising energetics. Gamma rays are thought to come from the most violent events in the cosmos, like stars colliding or exploding, he points out. What a surprise to find them shooting out of the cold upper atmosphere of our own planet. Something up there is accelerating low-energy particles of air to nearly the speed of light, producing gamma radiation and sometimes a cascade of antimatter. Rowland wants to find out what that strange, unknown something is. Fire Station is poised to crack the mystery. The experiment was delivered to the space station on August 3, 2013, by the Japanese robotic cargo vessel Kounotori 4. It has since been installed on the station's exterior by the station's robotic arm. All of the sensors were checked out at the end of August, and full-time science operations are slated to begin in early September 2013. For results from the cloud tops, stay tuned to science.nasa.gov.
Kinematics.com.
I think we're really at the beginning stages. That's one of the reasons that we need to create a global model, a complex model, because the pathways are so complex that we need the model to serve as a context within which we analyze and interpret the data. So some of those profound implications that I refer to, and I hesitate to even refer to them, but we would be thrilled if, as a result of our research, we found some electrical pathways that actually affected the climate of the Earth. A goal far in the future, but we do know that clouds are essential elements of the climate system. The way that clouds are created and the way that clouds evolve are somehow linked to the electrical properties of those clouds. If we can show that, that would be really something. We think that by pursuing an improved knowledge of the whole global electric system, that discoveries will emerge that we might not have even have anticipated. And that's the way basic research goes. It wouldn't be called basic research if we already knew what the outcome was going to be.
I'm from Penn State University and Communications and Space Science Laboratory. In that lab for the last 10 years we have been very actively engaged in development of theoretical understanding of transient luminous events in the Earth's atmosphere. So we work on a variety of subjects related to lightning and lightning behavior, lightning physics, and of course in the context of global electric circuit modeling. We want to quantify how much lightning contributes to the global electric circuit, for example in comparison with electrified thunderclouds and electrified clouds. There is a significant controversy in existing literature as to how much lightning contributes. So in some cases, some scientists actually claim 40% of the total current which is flowing in global electric circuit is contributed by lightning. So we want to actually understand and quantify actual amounts. Yeah, so there are many different research questions which are still remaining to be answered. So our group at Penn State actually pursuing research on gigantic jets. In other words, we're trying to understand how lightning discharge can escape from thundercloud and propagate toward the lower ionosphere. And lightning itself, of course, exhibits a very strong concentration of energy. The gas, the air, reaches very high temperatures inside of the lightning channel. And just because of this concentration, lightning is a very dangerous phenomenon. So there are still questions about why lightning, when it propagates upward in Earth's atmosphere, changes from this very hot and concentrated nature to this more distributed nature, resembling sprite streamers effectively. Okay, so we work on understanding of this heating effects. Of course, there are many questions remaining related to initiation of sprites. In other words, we don't understand very well why sprites are produced by very weak lightning discharges. So some weak lightning discharges surprisingly produce sprites. Not very often, but it happens. In other words, we're developing models, and through these models we're trying to understand better these terminology. And of course, in the context of global electric circuit modeling, we want to quantify how much lightning contributes to the global electric circuit, for example, in comparison with electrified thunderclouds and electrified clouds.
One of the processes in the ionosphere that affects the electric fields and the currents is the ionospheric dynamo. And this is the process where winds in the upper atmosphere, which are much stronger than they are in the lower atmosphere, they move this electrically conducting ionospheric gas through the Earth's magnetic field. And this is a process that generates an electromotive force and drives electric currents and produces electric fields. And by modeling the ionospheric dynamo, we are able to get information about the pattern of winds in the upper atmosphere. So another important source of electric fields and currents in the ionosphere is due to the connection with the magnetosphere that is far out into space, and the Earth's magnetic field extends far out into space and is influenced by the interaction with the solar wind, which is continually blowing out from the sun. And the solar wind drives motions in the Earth's magnetosphere. These motions get transmitted into the ionosphere, basically being mapped along the geomagnetic field. And so they end up most strongly at high latitudes in the auroral zones. During different types of solar disturbances, we can get very strong currents driven into the ionosphere, and this produces magnetic storms. And one of the concerns during storms, which is one aspect that we will investigate in this project, is that when there are very rapid changes in the ionospheric currents, we get electric currents induced in the Earth. Currents in the Earth can get into electrical transmission systems and disrupt power transmissions. And so part of our project is to understand a little bit better some of the factors that affect the generation of very strong electrical currents at high latitudes. In the lower part of the atmosphere, which for an ionospheric physicist means the stratosphere and lower atmosphere, there is still very weak electrical conductivity that's caused by ionization from very high energy cosmic rays that penetrate into the lower atmosphere. Also, as we get close to the ground, radon that is emitted from the ground in very small amounts, it does produce a very weak ionization of the air, so that the atmosphere is electrically conducting all the way from the surface of the Earth to the ionosphere, even though the conductivity is very weak. So the currents flowing in the lower atmosphere are much smaller than those in the ionosphere, but it is these currents that are connecting the lower atmosphere with the ionosphere. So the main source, we think, the main source of the fact that the ionosphere is a few 100,000 volts charged up with respect to the Earth is very weak currents that flow out of the tops of electrified clouds, thunder clouds and other electrified clouds. And over these clouds, current generally flows upward to the ionosphere. And then, since the ionosphere is much more highly conducting than the lower atmosphere, the currents can easily spread out horizontally. And in other regions of the Earth where there are no thunderclouds, the fact that the ionosphere is charged up a few 100,000 volts above the surface of the Earth means that a very weak current is flowing back through this weakly conducting atmosphere from the ionosphere to the Earth. We have a system where in localized regions current is flowing up to the ionosphere, and then over broad regions of the Earth we have a very weak current flowing back to the surface of the Earth.
Due to its molten iron core, the Earth has a magnetic field around it, just like a bar magnet. This magnetic field extends outwards into space, forming a big bubble that we call the magnetosphere. The inner layer of the magnetosphere, from near the Earth's surface up to 1,000 or so kilometers, is called the ionosphere because it is made up of particles ionized via radiation from the sun. In low-frequency radio astronomy, when we point our telescopes to the sky to measure the faint signals that travel through space to reach us, we need to take structures and perturbations in the ionosphere into account that might change these signals. We need a good understanding of the effects of the ionosphere to make sense of our data. Pictured near the surface, the Earth's magnetic field lines run parallel and come out at an angle to the ground. It has long been postulated that tubular plasma structures go along the magnetic field lines, and it is structures like these that can affect our astronomical measurements. Previously, people could only guess what they might look like, since no one has ever been able to image them. My name is Cleo Loy, and I am an astrophysics student with Castro at the University of Sydney. I have found that we can use a new type of radio telescope to not only detect these plasma tubes in the ionosphere, but to actually image them. And what's more, we can reconstruct their behavior in real time and in 3D. This is a very exciting world's first. The Murchison Wide Field Array, or MWA for short, is a radio telescope in the Western Australian desert. It consists of 128 receiver tiles, spread over a circular area roughly 3 kilometers across, that work together as one instrument. What makes it so special is its huge field of view, letting us observe a large patch of sky and all sorts of celestial objects as they flash or pass overhead. We use the MWA to study how the ionosphere shifts around the observed positions of objects in the sky and distorts them. A good analogy for this is the way lights at the bottom of a swimming pool dance around when the water ripples. We cannot see the water directly because it is transparent, but from the dancing lights we can determine the pattern of the ripples at its surface. Just like when we are looking at an angle down parallel train tracks, if you were standing at the site of the MWA, the Earth's magnetic field lines would appear to converge. What we saw with the MWA was a stunning distortion pattern that strongly coincided with the magnetic field lines. For the first time, we revealed the true nature of these structures as a vast array of plasma tubes, filling the sky in staggering numbers. The MWA's rapid snapshot capabilities allow us to make movies showing their motions over time. But that's not all. The MWA also has the power to see in 3D. When we look at an object, our brain combines the images from our two eyes, allowing us to judge how far away it is. So by analyzing the signals recorded by MWA tiles in the east, separate to tiles in the west, we give the MWA the ability to perceive depth. This has never been done with a radio telescope before. By using the MWA like a pair of eyes, the three-dimensional nature of the tubes springs into reality. We can measure their heights above the ground, see their steep inclination, and watch as they drift sideways towards or away from the MWA. This is a whole new way of looking at the sky.